Welcome to Planet Geo, the podcast where we talk about our amazing planet, how it works, and why it matters to you. Chris, how you doing today?
I'm doing great. How you doing, Jesse?
Oh man, I'm doing really well. I'm excited for today's episode, to be honest with you. But before we get to that, let's do some brief introductions. You are Chris Bullheis, a nationally recognized earth science teacher from the great state of Michigan.
And you are Jesse Reimink, one of my former students, now a professor of geoscience at Penn State.
And this is Planet Geo, a podcast where we talk about amazing aspects of our planet and why it matters to our everyday lives. Chris, how you doing?
I'm doing great. How you doing, Jesse?
Yeah, man, I'm doing really well actually this week.
All right, Jesse, let's get into it.
All right, yeah, let's do it. So, let's kind of give away the ending here. Why are the oceans salty?
Well, Jesse, come on now. The oceans are salty because of your hard water.
Yeah, that's it. That's the story, right? Done. End of the podcast. We can go home.
That's it.
But let's clarify this a little bit because you and I, when we say salty, it's not table salt necessarily what we're thinking of. So what are we talking about? We're going to talk about salts a lot here. What are we talking about?
Yeah. So salts in chemistry are ions that are dissolved in water. So most people think of sodium chloride or common table salt as a salt, and it is. Right. But it could be anything else that is dissolved in the water.
Okay, so when us geoscientists are talking about salts, we're talking about things like calcium and magnesium and iron that could be dissolved in the water, and potassium and sodium, which is common table salt.
Right.
Okay.
Yeah. All right, so Jesse, so then can you run it down for us then? What is hard water?
Hard water. Well, it's called hard water not because there's any physical property about the water that is hard in and of itself. It's because it's hard for soap to make suds. If you've ever showered or taken a bath or washed your hands even in well water at some campground or at your house, you can tell it's really hard to make a really nice lather in your hands, on your hands or on your body. And that's because there's a lot of stuff dissolved in the water. Most of it is calcium or magnesium, and these are ions, which means they're charged atoms that are in the water. They're dissolved in the water, and they really kind of destroy the surfactant properties of soap, which is the property that makes the suds. So for me, in State College, I live in central Pennsylvania right now, we have extremely hard water here. My coffee pot always has little white crystals all over it after I make a pot of coffee. That's a representation that you have hard water.
Okay. Wow, Jesse, you really like to talk, don't you? Okay, so if that's what hard water is, it's water that has these ions in it that react with soap and prevent it from doing its job. Where do these ions come from?
They come from rocks. They're really, it's water that's underground and it's interacting with rocks. It's dissolving rocks. And so, we're going to bring this back to why are oceans salty. It's really coming from the rocks. And this is a common misconception, I think, that you experience in your classroom quite a bit.
Yeah. So I'm going to stop you right there a second, okay? Because if I ask my kids, why are the oceans salty? How many of you have thought about this before? And I'll get a fair amount that have thought about this. Like, why are the oceans salty? And I'm like, okay, well, let's do this. And I think easily the most common answer I get is because of the rocks at the bottom of the ocean.
Oh, really? Okay.
Yeah, they know that there's limestone down there. They know there might be some gypsum and things like this, right? These other clastic sedimentary rocks like sandstones and shales. And so they'll say, well, the rocks that are at the bottom of the ocean make the water salty. And that's a good thought. Okay, yeah. It's absolutely backwards, but it's a good thought anyway. Okay, it's critical thinking. And
that's actually pretty intuitive of them to think that way. But you're right, it is completely backwards. Very wrong, very clever, though.
It is clever, yeah. So, yeah, that's what I usually get from them. Now, I think we need to come back to, all right, why do rivers flow all the time? Okay, and the answer is because most rivers are fed by groundwater. Okay, now groundwater is the third most abundant source of water on our planet. We have the oceans, has over 97% of our planet's water. Then you have glaciers and ice sheets and so on that have over 2% of the world's water. And then the third most abundant source of water is groundwater. And so this is water that's flowing through rocks below the surface.
So this is an interesting point that, again, not intuitive, is that water flows through rocks. So we often think of rocks as this big solid mass, right? But actually water is passing through many kinds of rocks. So maybe go into that a little bit.
Yeah, so it's passing mostly through sedimentary rocks, right? Mm-hmm. But groundwater is slightly acidic. Okay, and part of the reason is that it's acidic is because it dissolves carbon dioxide and it becomes a kind of a weak acid called carbonic acid. So you have this slightly acidic water that's flowing through and in between the grains in sedimentary rocks. One of the ways to identify a very common sedimentary rock, limestone, is by dropping some hydrochloric acid on it. You drop acid on this and it starts to fizz. It effervesces. And so
this is putting little droplets of HCl, hydrochloric acid. This is not dropping acid in a. There's different contexts for dropping acid, but this is not that. This is putting little bits of acid on a rock. And you know, this is a thing that many like biology or business majors might not really understand. Is if you get an undergraduate degree in geology, you know, we just have this little bits of weak acid laying around the lab all the time, and people are like putting acid on some samples to try and identify it, and then there's other students in the back of the room licking these samples to try and identify it. It's a really weird bunch, the undergrad geology majors, that's for sure, right?
Fair point. Yeah, I do take it for granted because I've been putting acid on rocks for a very long time.
Yeah, we do. We all do.
Yeah. So anyway, the point is that limestone, which is made up of the mineral calcite, is very soluble in acidic water, in acidic solution. And so as this slightly acidic groundwater is flowing through.
So let me interject there. Limestone. So this is a rock that's made of lime. I mean, as the name implies, it's basically like Tums antacids that you take. I mean, it's the same chemical composition as these antacids, right? Antacid, meaning you take it and it fights the acid in your stomach. Limestone is the same. It is dissolved in acid, therefore it kind of neutralizes this acidic stuff in your stomach.
I've actually used this in the field because I'm susceptible to reflux, and so I get heartburn very easily. And you know, when I'm in the field and I'm not prepared, I didn't bring my medication or whatever. I have done this before where I've taken a hammer and crushed up some limestone, put it in an Nalgene bottle, and drank it to get rid of my heartburn, and it works.
Hey, you are showing. I mean, this is the chemistry behind hard water right here in action. Is your dumbass forgetting your antacid pills and just crushing up some limestone?
It works though. It's kind of I don't know.
I
give myself credit for that because you wouldn't think of it. Anyway, so this acidic groundwater is flowing through, and it will selectively dissolve calcium carbonate, which is the chemistry of the rock limestone. And so what it does then is it carries this water, which remember, groundwater feeds rivers. And this is why rivers flow even after long dry times at the surface, because it's being fed by a much more abundant source of water below the surface.
Right. So even though it won't rain for many months in some places, the water's coming from the ground. The groundwater is interacting with these rocks. It's slightly acidic, so it is dissolving some of the limestone, and it's absorbing some of these ions, dissolving them, and then carrying them downstream through the river system.
Yeah. Now, you're probably, if you're thinking about this, my students will say this too. Well, yeah, but Mr. Boyce, the rivers don't taste salty. And that's a really good observation. Okay, well, yeah, they don't. They have these salts in them, but it's a pretty small amount, right? So the groundwater is feeding the rivers. The groundwater is what's bringing these dissolved ions to the rivers. But then what is the destination of every single river? What is the ultimate destination? It's the ocean, right?
They're all rivers flow downhill, and we use sea level as a baseline measurement as that's zero elevation for a reason, because that's where all rivers end.
Right. So here's my thought, right? And when we started this whole thing of these three underlying questions that we wanted to tackle in this episode. What is hard water? We've answered that. Why do rivers flow all the time, even after long dry spells? Well, because they're being fed by the groundwater. what's in the water are salts that was brought there by groundwater.
Right.
Okay. Now, that leads us to the third thing. Why are the oceans salty? What feeds the oceans? Where does the water come from?
Well, we kind of just touched on it. The water comes from the rivers. So the rivers are flowing. The rivers are coming mostly from groundwater. Groundwater is interacting with the rocks. They flow through the river. The river ends up in the ocean. So our oceans are supplied by the major rivers around the world.
How does water leave an ocean basin? There's only one way.
Mostly by evaporation. The oceans are evaporating all the time, huge amounts of surface area, and it's all evaporating. This is where we get clouds and rain. All the water in our atmosphere is coming from mostly evaporating off the ocean surface.
So if you compound this over time, right, these salts are being added to the oceans bit by bit by bit by rivers that carry these salts. But then evaporation, when the water evaporates, what stays behind?
What's evaporating is actually the H2O molecule. The salts don't really evaporate. And salts, meaning the dissolved ions that are not hydrogen and oxygen, those mostly stay behind in the water. And so you evaporate the water H2O molecules now go into the atmosphere in a gas phase. They make clouds. Those clouds migrate around. They rain on the continents. That rain then seeps into the ground, interacts with the rocks, and then we've started back at the cycle of making hard water again. So we're making hard water by rainwater going and seeping through the rocks. It's slightly acidic. It dissolves parts of the rock, and then it flows through rivers back to the ocean. So we're kind of completing the cycle here, but there's a missing link in the cycle in that the salts are not transferred through that evaporation process. So this is effectively distillation. I mean, this is it's not unlike, the way you make maple syrup or the way you increase the alcohol content of liquor and stuff like that.
So because over geologic time, it gets compounded. The salts stay and the water gets evaporated. But this cycle continues and more salts are added by the rivers. The water evaporates and the salts stay. So compounded over time, the oceans are salty. That's what's going on. So why are lakes, Jesse? Why are lakes not salty?
Well, because they haven't had enough time to develop this saltiness to them. They'll be a little bit more salty than the rivers, but they haven't been there for that long. The Great Lakes around Michigan have been there for a few tens of thousands of years, 15,000 years. The oceans have been around for much longer, billions of years. And so they've had billions of years to take ions that are dissolved in the groundwater that are making hard water and absorbing those, and then that gets concentrated in the ocean. So they've had much longer time than lakes to get salty. Right.
So let's circle back then to what my students say. Why are the oceans salty? Well, because the rocks make them salty. Well, actually, that's not what's going on. See, when the oceans get saturated, and what this means is saturation is like a sponge that can't soak up any more water. It's saturated with water. Well, when the oceans are saturated with salts, they can't handle anymore. They start to lay them down. We call this in chemistry, they precipitate these rocks. They'll precipitate limestone, they'll precipitate gypsum, they'll precipitate halite, which is rock salt. As the water gets saltier and saltier and saltier, it reaches a point where it can't dissolve anymore, and it starts to then lay down the rocks. So the flaw in the logic is the rocks are there because the water's salty. Not the other way around. The rocks don't make the water salty.
Right. So if we bring it back to hard water and what you get out of either your well or if your city water is pretty hard. What's going on there in the chemistry, and what's actually happening in this hard water that you see the repercussions of it in your house?
Yeah. Well, most people that have well water, they need to have what's called a water softener. Okay, now this is where the terms don't really make sense because we think of, hard water. Well, that's because it doesn't lather easily, right? So shouldn't we call it a something like easy water then? If it's hard water because it doesn't lather, shouldn't it be easy water? But now we don't do that. We actually further the misconception. Let's call it soft water now.
Yeah, exactly.
It's so irritating to me. It doesn't make any sense at all. It furthers this misconception that hard water it has some physical hard property to it.
Right.
I don't know. Anyway, so yeah, a water softener. What does a water softener do? Well, it effectively removes the calcium and the carbonate. It removes these ions from the water, allowing the soap then to do its job, which is form a lather and clean. Okay, so we call that a water softener. Now, if you don't soften your water, okay, if you don't remove these ions,
right?
What is the effect?
Yeah, what happens? What happens? So if you don't do that, what happens? Why do you need that freaking expensive water softener in your basement?
You do. Well, first of all, I like to get clean, and so I need a water softener so that I can make suds in my.
I don't know.
I'm
not sure how clean you ever get yourself. You're kind of a dirty
you
human being.
I know. You're right. But what can be the effects of this? Well, if the water softener isn't doing its job, then you'll start to, in your toilet bowl, for instance, water's going to evaporate, which is going to cause then that water to get saturated with limestone, and it'll precipitate then as this kind of like crud around your toilet bowl. It doesn't look good, and it's really hard to remove because it's a rock.
Right, it's a rock. It's limestone. It's your Tums, tablets. It's in a rock form, so it's incredibly hard to dissolve that.
Yeah. So anywhere you have sitting water, you're going to have that happen, or even on the inside of your pipes. And this is where it gets very costly, and a big concern actually is if you get lime precipitated on the inside of your pipes. It restricts the flow of water then. You don't have the water pressure you need because you have lime scale on the inside of your pipes. It can be a problem, to say the least.
Yeah, and so this matters. Big factories that have hard water, they have to spend a lot of money to soften that water because otherwise you're getting these deposits on the inside of your pipes. And there's pictures online you can go to. We'll put a link in the episode description here to a United States Geological Survey website that shows a couple pictures of what a pipe looks like with these lime deposits on the inside, and it can be a huge problem. So it's much more cost efficient to soften your water up front than to deal with the narrowing of these pipes and to destroy industrial scale tools and machines. The other thing that it can affect at a homeowner scale is if you have too many deposits on like your pans and stuff like that, it can really reduce the heat conduction properties of your cooking pans.
Wow, look at you go. That is a really good point. Every once in a while you surprise me with your own intelligence.
It's rare. It's once a year at best, probably, but
it's not common. That's why I marked on it for sure. But that's true. I mean, rock is not a good conductor of heat.
No, exactly. So the pure metal is much better. So if you get too much of this lime deposit on your pan, it's not going to cook as well. So next time you're kind of bitching and moaning about your water softener, you can think about the relationship between hard water, why the oceans are salty, and where that water is actually coming from. I live in central Pennsylvania, and our water it's municipal water, but it's groundwater, and there is a lot of limestone in this region. And so we get our water, and it's coming from the ground, and it's very, very hard, which means that it deposits stuff all over the place.
In Michigan, most people that if they have city water, they're getting their water from one of the Great Lakes, right? And as we already talked about, the lakes are not really full of hard water because one, they're not as old. Two, the lakes have more than one output. They have more than one way for water to leave the system. The Great Lakes are drained by the St. Lawrence River. And with the oceans, that's not the case. It's evaporation. That's the only way. And when water evaporates, the salts stay behind, so the oceans get saltier.
Right.
Okay, that's not necessarily the case with most lakes. They have multiple inputs, multiple outputs.
That's right. Most lakes have an outlet. Though lakes that don't have an outlet get pretty salty. So, for instance, what used to be where the Great Salt Lake in Utah used to be an actual lake, and it had no outlet. So it just built up salt and salt and salt, and then it deposited these salt beds in it. The Dead Sea also has no outlet. So rivers flow into it, nothing flows out, so evaporation takes over, and you just concentrate these salts, and it makes it extremely salty.
So I think these issues or these geologic concepts that we're talking about, they also tie into ocean acidification, right? Jesse, what do you think? You agree with that?
Yeah, no, absolutely. I agree completely. I mean, we've been talking about oceans, why they're salty. We've been talking about groundwater, that it's slightly acidic, and so it's therefore dissolving all these rocks and bringing them to the oceans. And, in the news, you hear a lot about ocean acidification. And this is related to climate change and CO2 and all this stuff. So let's just hit that real briefly to end up here, to tie this all together.
Yeah. So why would the oceans become more acidic? And then why does that matter, right?
Right.
Well,
right.
Back to the COVID episode, we talked about emissions of carbon dioxide. Well, when you have increasing levels of CO2 and more carbon dioxide then gets dissolved in the water, which makes the water more acidic.
Yeah, let me interject with a statistic there. 30% of the CO2 that is put into the atmosphere is actually dissolved into the oceans. So 30% of that, no matter what, if we put 100 million tons of CO2, if we put 3 billion tons of CO2 into the atmosphere, 30% of whatever that number is going into the oceans. It's dissolved. It's no longer CO2, but it's dissolved as like bicarbonate into the oceans.
Correct. So that carbon dioxide then is turned into carbonic acid, which is a pretty weak acid. More carbon dioxide equals more acidic oceans. Now, the question is then, why does that matter? Well, this gets down to then what we talked about with what rock and what mineral is dissolved by weak acids, and it's limestone, right? Well, most of the organisms that make shells and build things in the ocean, like corals and these shelled marine organisms.
Think clams and oysters and things like this that we like to eat, what their shells are made of.
Yeah, if you put acid on one of these organisms, it's going to fizz like crazy because it's made of calcium carbonate. It's made of limestone or the mineral calcite. So if the oceans become more acidic, these organisms then have a harder time making their shells because they're being dissolved by an increasingly acidified ocean. And that then has major implications.
That's right. So if you enjoy eating your oysters or clams or whatever seafood, these organisms, these creatures are going to have a harder time making their shells. And people have tested this. People have said, okay, let's put a little bit more acid. Let's put a little bit more CO2 acid into the ocean, into some tank. Let's put some oysters in there. And basically the conclusion is that their shells dissolve within about 45 days. And these organisms have a much harder time just living because they have to put more energy into creating these shells because they're less stable in the now more acidic ocean.
Next time you think about hard water, think about where that comes from. Hard water comes from the ground, which then feeds the rivers. So the rivers keep flowing. The rivers make the ocean salty. And these salty oceans lay down rocks. It's a beautiful thing.
With that, thanks for listening. Again, you can find us on all the social medias at Planet Geocast. And please reach out. Please tell us what you think about these episodes. If you have some good ideas for future episodes, let us know. Our email is planetgeocast@gmail.com. We've already had some good suggestions from listeners, and we'd appreciate more of them. So,
keep the feedback coming.
Yeah, we love it. With that, take care, everybody. We'll talk to you soon.